Hello and welcome to the lab. On the bench today we have the Hewlett-Packard 3400A RMS Voltmeter. I wanted to do a quick teardown and highlight some of the interesting features and circuitry of this instrument, and then we're going to do a quick repair. So if that sounds like something you'd be interested in, stick around and let's get started. So taking a look at the front of the instrument, the 3400A has a toggle switch for power and a neon line indicator to indicate that power is applied. It has a BNC input jack, a standard BNC input jack with an input impedance of 10 megohms. It has full-scale ranges from 1 millivolt all the way up to 300 volts in 10 dB steps, and it also has a frequency response range of 10 hertz to 10 megahertz. It has a mirrored scale that displays both decibels and voltage ranges. If we take a look here, the center of the instrument should have a mechanical zero set screw. That is so that when you turn off the instrument and no input is applied, the needle should indicate 0. And the needle does indicate 0 here, but you can see that the mechanical 0, if you look closely, you can see that the mechanical 0 set screw is broken and really does not exist. That was a common failure actually in these units. And that's the repair we're going to try to attempt to do later on towards the end of this video, is I'm going to try to replace this meter movement with a different one that has the mechanical 0 set screw. So that's what we're going to do at the end of the video. Let's take a quick look at the rear of the instrument. It's simply they list some of the main specifications of the instrument on a little plate. Has a DC output jack, which is very useful. It outputs 0 to -1 volt DC, which directly corresponds to the meter indication on the front panel. And that's very useful if you use this instrument as you can connect it to a DC digital voltmeter, and you can turn this instrument into a digital AC voltmeter. Has a line fuse, a standard line input connector, a selectable line voltage, either 115 or 230 volts. And a serial number plate on the back. So that's the 3400A. Before we open it up, I'd like to take a look at the block diagram of the instrument to try to explain some of the circuitry before we get into it. So let's take a look at the block diagram of the 3400A. Has an input connector over here, input attenuator. The input attenuator is used for ranges 1 volt and higher. It divides by 1,000. On the lower ranges, the input attenuator is switched out of the circuit. The impedance converter A2 assembly, that's an interesting circuit. Normally, on an instrument such as the 3400, you want to use a special type of transistor called a JFET, J-F-E-T, a junction field effect transistor. And that is the type of transistor that will provide a high input impedance to your instrument so that you will not load down the circuit you are trying to measure. You won't draw any current from the circuit you're trying to measure. JFETs were not readily available when this instrument was designed. So they wanted to use transistors, but in fact, they ended up using a vacuum tube at the input in the impedance converter instead. They used a special type of tube called a nuvistor, N-U-V-I-S-T-O-R, nuvistor. Instead of using a JFET, which were not readily available at that time, they used a tube. So it's not really a solid state instrument. It actually has a tube inside of it, and we'll open it up and show that to you. After that comes the second attenuator. That's where most of the range switching takes place. So it operates in 10 dB steps to give you the correct 1 volt full scale output from the instrument. Video amplifier Has nothing to do with making a video. It's just in those days, anything that wasn't an audio amplifier with a bandwidth of 20 kilohertz, they called it a video amplifier. So this is a 10 megahertz bandwidth amplifier. Okay, so that provides the 10 megahertz bandwidth for the instrument. There's a thermocouple pair. Now, this is the secret to the whole instrument that causes it to be an RMS responding voltmeter right here. Most AC voltmeters are average responding, and they use a simple diode detector circuit to change the AC voltage to a DC voltage that the meter output can measure. This instrument uses a thermocouple pair, and that is a heating element bonded to a thermocouple. And so the heating element is applied, the voltage is applied to the heating element, and it warms up the thermocouple, producing a very tiny DC output voltage proportional to the heating in the temperature increase in the heating element. In other words, proportional to the RMS voltage that's applied at the input. That small DC voltage is applied over here to the next section of the circuit called the chopper op amp. That's another part of the circuit we're going to take a look at. Chopper op amp is a high gain amplifier. Now, especially in those days, when you had a voltage on the input, which is on the order of, say, 10 millivolts, you could drift in the high gain amplifier. You had to multiply that by at least 100 in order to get 1 volt here at the output, times 100 to get 1 volt, right? The problem with that is that even a small amount of DC offset that is drifted due to temperature or change or thermal instability or who knows what in this amplifier is going to be multiplied by 100. And in fact, if you drift by 1 millivolt, it'll be 100 millivolts of drift in the output. And that will be a 10% error, and that's unacceptable. Because you're measuring such a small voltage, DC voltage, and you're amplifying it by such a large amount, using a DC amplifier is not the way to go. So instead, what they decided to do was use a chopper amplifier. What that is they chop up the input, convert it from a DC, low-level DC, actually to a square wave, which can then be passed through a high-gain AC coupled amplifier and amplified by a factor of 100 without any concern to the DC offset drift inside the amplifier. At the output of that, they convert the square wave back to a DC at the output. It demodulates, this chopper demodulates the square wave and turns it back to a DC that's amplified by a factor of 100. I'm just saying 100 as an example. Okay, so that's what we have here. So now we have a 0 to 1 volt DC amplifier. That demodulated square wave is filtered to remove any noise that's in the system. Okay, we're going to take a look at that chopper op amp as well. And then it passed through to an output amplifier to give you a low output impedance to drive the meter and to drive the DC output jack on the rear panel of the instrument. That's 0 to minus 1 volt DC. And like I said before, if you connect a digital voltmeter to this output jack, you now have a digital AC voltmeter that's good from 10 hertz to 10 megahertz. So let's open up the instrument and take a look inside of it. Okay, first things first, if you're going to be working on a piece of test equipment, make sure you unplug it. Very, very important. You don't want to get zapped. Okay, now, if you're going to be working on a Hewlett-Packard instrument from the 1970s or 80s or 60s, you need to get yourself posi drive screwdriver. These screws that are in here look like Phillips screwdrivers, but they're not Phillips. They're a slightly different shaped head, and it's called posi drive. You have to use a posi drive screwdriver. If you try to use this Phillips screwdriver, it may work in a pinch if the screws are not too tight, but you're going to end up eventually damaging your nice piece of vintage test equipment. Use a posi drive screwdriver. They're still available. Now, while I'm tearing this thing apart, I thought that maybe I would talk a little bit about the HP 3400A. It was made from 1965 all the way up until 1992. It was made in Loveland, Colorado. This particular instrument, this one, was made in 1978, which actually happened to be the year I graduated from high school. Take the top cover off. Let's take the side covers off. The Hewlett-Packard 3400 was made starting in 1965. It cost a list price of $525, and that was 1965. So it was a pretty expensive instrument. In the last year it was made in 1992, it cost $2,195. Still pretty expensive instrument. I paid far less than that for this thing. I think I paid, I don't know, $80 or something for this one. There's so many of them were made, tens of thousands of them, almost 100,000 of them were made over those almost 3 decades of production. So there are many of them available, and they're all pretty inexpensive today. But it is a very important piece of test equipment, and I think that if you want to build a vintage lab like mine, it's necessary. You almost have to have a 3400A. It has countless uses even today. Of course, it's obsolete today, but if you like vintage test equipment, you should get one of these. They're really, for less than $100, you can get one that's in working condition. They were built like tanks, so they never fail, almost never. And when they do, they're easy enough to fix. So I'm going to continue stripping this thing apart. You don't need to see me pulling out all the screws, and I'll come back when it's done. And there we are. Okay, so this is the inside of the 3400A. You see the power transformer here. You see it's rather large because we have to generate a higher voltage for the tube that I mentioned earlier that's in here. We have some power supply pass transistors on the heatsink on the rear panel. Behind that, we have power supply board, all these electrolytic capacitors and so on and so forth. There's some diodes, some transistors and stuff in there. On the left side, we have behind the input connector front panel, we have the input attenuator that has the 10 megohm resistor in it to provide the 10 megohm input impedance for the instrument, and this also divides by 1,000 for the higher ranges. For the lower ranges, it's not used. Following that, we have the impedance converter. This is the thing that I mentioned before, the assembly I mentioned before, that should have a JFET in it. And instead, what they did was they put in a tube. And here is the new Vista tube. This little thing on my finger's pointing to right here, that is the tube. I'm going to show that a little bit later in the next segment. Over here is the video amplifier, and behind this metal case are the thermocouple, the thermal converters, and that's what changes it from a regular voltmeter into an RMS responding voltmeter, those thermocouples. So we're going to open that metal case up and show you what's inside of there as well. Behind that, the other assembly we have here is the chopper stabilized op amp assembly. Down here, I don't know how well you can see. Let's see if maybe we can zoom in a little. All right, here where my finger is pointing, you see those two gold things? Those are the two parts to the chopper stabilized op amp. That's the chopper that actually converts the low level DC signal into a square wave that can be amplified by the AC amplifier in the video in the op amp here. The op amp, of course, was not made with integrated circuits because they didn't really have them at that time. This is all made with all discrete transistors, but it's still an operational amplifier. It's not an op amp chip like you would think. In later models, they actually did use an op amp chip. But these choppers, what that actually is two neon light bulbs inside of there that flash at a rapid rate onto photoresistors. And what that accomplishes is the chopping of the signal to turn it into a square wave. Over here we have some calibration trimmer pots, 1/10 scale, 1 full scale, and meter. And you see some small factory selected resistors that are added not on the circuit board to make it to compensate for various differences in manufacture. So those parts are hand selected to make it meet all the specifications. We have a couple of big chassis mounted electrolytics. I've never seen them go bad, although they might eventually, but I almost never see any of these go bad. So I wouldn't worry about them too much. Down here we have the other attenuator, the second attenuator that selects all the various ranges, and you see some compensation, trimmer capacitors, and so forth for frequency response and flatness. There's also compensation here on the preamp, on the first attenuator, the input attenuator, some trimmer capacitors for frequency response. So I'm going to take a look at the new Vista first, and then we're going to take a look underneath this cover to see what the thermocouple assembly looks like. I don't think I will be able to really pull apart the photo chopper assembly to show you what's inside of there. I would like to, but that might cause problems in the long run. So we're probably just going to have to zoom in and see what we can see down there. There's not really much to see. You see it's an aluminum case with two different photo cells in it, and when you plug it in and turn it on, you can see around where the gold wires enter those two golden photo cells. You can see the neon light bulbs flashing inside of there when it's turned on, but I'm not going to demonstrate that here today. Okay, let's see what we can. So I removed the new Vista tube from its socket, and this is what it looks like. You can see it's actually a tiny miniature vacuum tube. It's got contacts on the bottom that plug into the socket, and it is almost as tiny as a transistor, but it's actually a vacuum tube, not like the glass ones we're used to seeing. But this is all they had available when the design of the 3400A was first developed. They didn't have the JFET at that time, so they had to use something that would work to give a high input impedance to the circuit. So then a Vista was used. So underneath the metal cover are these two glass capsules, and inside of each one is a heating element thermally bonded to a thermocouple, which is a pair of dissimilar metals that outputs a DC voltage proportional to the temperature. So the heating element is what measures the actual RMS input voltage, and the output of each of the thermocouples is a very tiny DC voltage. Now, the two thermocouples are connected in series to improve the sensitivity, but this little device with the two glass capsules is actually where the magic of the RMS voltage measurement takes place. So I placed the thermocouple element under my microscope, and I'm trying to get an image of what actually is taking place here. I apologize for the poor quality of the image, but I'm using my smartphone to take capture the image off my microscope's screen. So if you look, this small squiggly line going from left to right between the two electrodes, that's the filament, the heating element that actually measures the input signal. And the two V-shaped wires coming down towards the bottom, that is actually the thermocouple. And where they join in the middle is the junction where the heating element warms up the thermocouple. The thermocouple senses the amount of heating power in the filament, and therefore the equivalent, it outputs a small DC voltage equivalent to the RMS value of the heating voltage supplied through the heating filament. I don't know if you can actually see this very well, but that's what I'm trying to get an image of here. So I mentioned earlier that these 3400As are readily available for not very much money. So I happened to acquire one to use as a parts unit, and I removed the meter movement from that second instrument, and you'll see that it does have the set screw for the mechanical zero that's still intact and not broken. So I'm going to try to replace the entire meter movement in my 3400 with this meter and solder it in place on the two terminals on the back, and bolt it in place with the screws on the sides, and we'll have a repair for the broken mechanical zero set screw. And I'll come back when that's completed. Okay, so I've completed the repair, and as you can see, my mechanical zero set screw is now like it's supposed to be. The only thing left to do is make the adjustment for a full scale of 1 volt. So I input exactly 1 volt from my voltmeter calibrator, and I'm looking at the output on the rear of the instrument with my digital voltmeter. Now I'm going to make the adjustment, as it's very, very ever so slightly reading high. Let's make that, whoop, oh, pretty sensitive, pretty sensitive. Looks like that pot might be a little bit dirty. Let me tweak it again. Here we go. Now it's reading a little bit low. Let's keep going. There we go. That's about as perfect. I don't know how it shows in the camera, but that's perfect to my eye looking at the meter. Let me just check the 1/10 of full scale. So let me set my calibrator to 1/10 of a volt. It looks like 1/10 of a volt to me. All right. She is adjusted and calibrated and good to go. I'm going to run through the performance test on this instrument, but I believe we are done. So thank you very much for watching, And if you like what you see, please click like and subscribe and click that bell icon so you'll get to be informed of when I make my next video. And thanks again for watching. Bye-bye.